So if you look at this slide, I think this slide, a lot of us will probably able to see that this is something that we have transitioned over the years, right? A lot of us having been in the IT industry for a long time. So this slide actually shows our progress over the years, from a perspective of how and where we deploy our application. So if you recall, right, from the very beginning, we deploy the entire application code on dedicated machine, right? On dedicated compute server or even mainframe. So we use specialized OS, and the kernel was also specially designed for the hardware. So as such, there were a lot of heavy dependency between the application code and its framework, and the OS on the kernel as well. So this deployment model, it worked well for us, for a long time, but as we have seen, right, such a deployment model, it could take months for us to roll out a new application. And sometimes they were also often low utilization in the hardware resources. And the entire deployment, it could not be easily ported over to other environment. So you know that when you deploy a code in a piece of application on the mainframe, on AS400, for example, right? So there's no way that you can easily port this over to an x86 environment. So there's a lot of work required to do that. Then over time, with virtualization, we turned to virtual machines, where we saw improved utilization by sharing the hardware resources with VM using a hypervisor software. So this has significantly improved the deployment time. So we have reduced the deployment time from months to days down to minutes. However, with virtualization, we now still have to deal with both the guest OS and the host OS layer below. So there's a guest OS for every virtual machine. And there's also dependency between the application code and the guest OS. So today, with containers becoming almost the industry standard approach for application deployment, we can now achieve application deployment speed down to seconds. So there's no more dependencies between the application code and the guest OS. So rather that dependencies can be built into the application code and its container image. And then that image can also be optimized. So we can deploy containers consistently across different environments with a standard container runtime, right? So you can use Docker, you can use CRI. So there are many different containers runtime out there, right? So Docker has been one of the most popular runtimes so far. And we can run these containers on compute hardware, which can be a virtual machine or dedicated bare metal server. So containers are not intrinsic or primitive features of Linux. So instead, their power to isolate workloads is derived from the composition of several technology. So one foundation is the Linux process. So each Linux process has its own virtual memory space, and this is separate from others, and Linux processes are rapidly created and destroyed. So containers use Linux namespace to control what an application can see through the process ID numbers, directory trees, IP addresses, and so on. So Linux namespaces are not the same thing as Kubernetes namespaces. So for Kubernetes, right, the container use Linux C groups to control what an application can see. The maximum, also to control its maximum consumption of CPU time, memory, I/O bandwidth, and other resources. And finally, containers use a union file system to efficiently encapsulate application and their dependency into a set of clean minimal layers. So just a bit of explanation about how containers work under the hood. And to answer the question of why we choose containers for application code deployment, there are many benefits of doing so. So for example, with containers, we can have consistent environment. So when we deploy our application code in containers, in the cloud or on premises, it is expected to run consistently in any of these environments. So secondly, we can also achieve higher application portability. So with containers, we can run it anywhere, whether it's on premises or in the cloud. So all you need to do is just move the container images to the destination. So next, containers allow us to adopt the microservices framework where we can break up a large monolithic application into smaller pieces of code that makes up the entire service. So this is called microservices. So these microservices, they communicate with each other using API or the RPC, right, framework, and we can achieve a higher application isolation. And with container, we can also be more resource efficient on our infrastructure. So containers are lightweight compared to the larger form factors of virtual machine. And containers also allow our developers to become more efficient by integrating the build process into your DevOps and the CI/CD. And our developers can deploy their application code in containers within seconds. And this velocity allows them to innovate for your business. Well, I've said all the good things about containers so far, but of course, on the flip side, there are also challenges that we need to solve, right? So there are challenges when it comes to running container, especially when we start to do this at scale. So when it comes to deploying our container images, we need automation, right, to support automated rollout and rollback when things go wrong. So we cannot expect to be deploying thousands of containers manually. So we need a lot of automation to help us to scale. So we need to understand our application resource requirement so that we can also maximize our resources by using methods such as bin packing. So this word bin packing, it basically refers to how we can pack the most number of container into one compute resource, such as virtual machine or your dedicated server that hosts the container. And we also need advanced method to ensure our container runs smoothly in production, such as self-healing when things go wrong. And service discovery, load balancing, auto-scaling. So this refers to a networking mechanism in production environment that allow client to actually discover the services that are running in different location. And load balancing is about how we load balance traffic efficiently across location, right? Serving the same application code. And auto scaling refers to automatically scaling out the infrastructure to handle periods of high peak loads. And then finally, storage management, we also need to think about that. So this is how we handle the requirement of certain application workload that require specialized or stateful storage. So as a response to all these challenges that we need to solve in order for us to actually get onto this hybrid cloud strategy, so Google helped the industry created Kubernetes. So if you're new to Kubernetes, so let me just do a bit of a introduction. So Kubernetes is a container-centric management environment. So Google originated and later on donated it to the open source community. And now it is a project under the vendor neutral cloud native computing foundation. So Kubernetes helps to automate the deployment, scaling, load balancing, logging, monitoring, and other management features of containerized application. So these are the features that are characteristics of typical platform as a service solution or PaaS. And Kubernetes supports what I call as decorative configuration. So basically, when you administer your infrastructure using this decorative method, you basically describe the desired state you want to achieve instead of like issuing series of command one by one to achieve that. So let me give an example. So I can say that I want to deploy this application with let's say 10 sets of replica, right? So each of this actually is a stateless container running the same application code. So when I tell the Kubernetes container orchestration system that I want you to deploy this application code with 10 sets of replicated pods, it will spin up 10 container pods and you will try to maintain it at 10. So if any point of time when one of these container pod dies, right, it crashes due to some troubles, it will then create a new one to replace the one that has just crashed, right? So you will always try to maintain it at this whole entire environment, in the desired state that you have actually tell it to maintain. So this is what we call as a decorative decoration. So Kubernetes' job is to make the deployed system to conform to your desired state, and you will try to keep it there, right? Despite of failures, you will try to do self-healing and try to maintain it at your desired state. So decorative configuration save us a lot of work because the system desired state is always like documented in the system. It also reduces the risk of error. And one of the primary strengths of Kubernetes is its ability to automatically keep a system in this desired state that you declare. And then, of course, Kubernetes also allow that step-by-step command line to be issued, right? So it allows this thing called the imperative configuration, whereby you can issue commands to change the system state. So as you can probably tell by now, containers give us many benefits. But to run the containers efficiently, we need a powerful container orchestration system, such as Kubernetes, to do the job. So Kubernetes is powerful and is open source. But if you are thinking of like implementing and deploying this system yourself using open source, all right, so there's not a lot of organization that has chosen this path for their production environment, because this requires a lot of technical resources. So you need to have a large team of people to help you to maintain this infrastructure, because you need to think about like patching, the software, upgrading the software when there's a security vulnerability that is announced by the upstream. So this requires you to maintain a team of resources to actually maintain this. So for Google to help our customer to adopt containers and to run them efficiently, Google created GKE. So there are many reasons why customers around the world choose GKE. So for starter, it's easy to get it up and running. So Google automates the complexity of deploying your own class, your first Kubernetes cluster. And if you go to the Google Cloud Console user interface, you can stand up a cluster between minutes by just using the UI. And then next thing is about simplified management. So this is where Google will handle all the upgrades, security patching, and auto repair of your cluster for you. And then you don't need to worry about all these details. So GKE is also very suitable for highly optimized workloads. So for example, you could have some workloads that require hardware resources, such as GPU or TPU acceleration, or you need some kind of integration with like machine learning or artificial intelligence frameworks such as Kubeflow. And you can also run specialized workload that require stateful storage, right? So like databases. So GKE also supports high availability for your cluster to handle any single zone or even multiple zone failure. And GKE can also handle auto scaling of your cluster for you, so that during periods of high peak load, it can then scale your cluster. And then during periods of low peak load, it can then automatically scale in your cluster as well. So it will do this transparently for you. So GKE can scale to any workload. And also want to mention that Google is today still the leading contributor to the open source community and also many upstream Kubernetes projects. So later in my presentation, I will be covering Anthos, which is the evolution of GKE to support hybrid and multi-cloud environment. So I'll just show you a quick look of how this Google Cloud Console UI looks like if you are new to it. So from the UI, you can start a GKE cluster with a single click, and you can also view all your clusters and all the workloads, right? Your application workload from this single pane of glass. So it is that easy. And GKE can also offer our customer with a simplified management and integrated monitoring. So through the Google Cloud Console, customer can have comprehensive observability of the workload and services across all their clusters from one single pane of glass. And many customers who runs Kubernetes have also adopted open source Prometheus for monitoring, right? So they have this Prometheus in their on-premises. And we can also support seamless integration with Prometheus, where you can also send your Prometheus raw logging, to the Google Stack drivers, and then integrate this with cloud monitoring and logging. So you can continue to run your open source software anywhere, and then we can integrate that for you seamlessly. And then over time, perhaps you want to consolidate your monitoring tool, with the Google Cloud Monitoring, so that it can help you to reduce the cost of using different tools. And with integrated cloud monitoring, Google brings its SRE best practices into your environment and into your operation team. And when it comes to managing your Kubernetes software releases, GKE offers a customer with many options. So we have the concept of release channel, where the customer can decide whether they want to use the latest and the greatest release via rapid channel. So they can select rapid channel, and this is where Google will always upgrade your cluster to the latest and greatest upstream releases. But for production environment, we always recommend our customer to choose either the regular or the stable releases, which are more mature. So regardless of which option you choose, so Google can help you to manage the software release upgrade of your cluster transparently for you. So as I briefly mentioned earlier on, GK also offer hardware acceleration option to support specialized workload, which require things like GPU, TPU, or local SSD for stateful and high performance storage. And GK also offer Windows, as many of our customers today, they have packaged the application like using .NET, and then this application still runs on Windows today. So customer can also upgrade their legacy Windows into containers, and then they can then move on to the path of building cloud-native microservices architecture based on .NET Core. And in the meantime, we can also help you to run both your Linux and the Windows container pod side by side in GKE. So GKE can also scale your cluster to support any workload requirement. So we support the full options of vertical pod auto-scaling, horizontal pod auto-scaling, cluster auto-scaling to automate the scaling out and in of your cluster based on your traffic and the workload utilization. And we also have something extra that other cloud providers today they are not able to provide. So example is a node auto provisioning. So this is an option where we can help you to optimize your resource utilization by helping you to provision a new node pool, right, using the most cost-effective machine, right? So maybe your workload that you have just scheduled onto your cluster, this workload doesn't require that much computing resources. So we will always create a new node pool with all the with all the VMs in the node pool based on the cheapest machine type to help you to save costs. So this can help you to handle the increased load, by helping you to also maximize your resource utilization. And also, just for the record, just to mention that somewhere in the world, we have also scaled GKE to a cluster with 15,000 worker nodes with one of our customer. So this gives us a bit of this bragging rights, but it's not common that every customer, it's not every GK customer out there today runs a cluster with 50,000 nodes, right? So we have actually proved that we can actually help one of our customers to get to that cluster size. So this was a record somewhere. And finally, on the networking part, we also support different options on Google Cloud to bring that ingress traffic into your cluster. So we support internal HTTPS and external HTTPS load balancing, and traffic director for directing traffic into your HA cluster located in different cloud region. And Anthos Service Mesh is, as I mentioned earlier on, is a Google curated versions of open source Istio that allow you to deploy a Google supported version of Service Mesh for your cluster.